corresponds to propositions like A is in delta. Then you have some state which is a point interface, and there are two possibilities. Either this point lies in the subset of the corresponding proposition, or it does not. So it makes the proposition true or false, and this is exactly what a pure state does. If we want a similar thing in this framework, then we would need a morphism from the subobjects of sigma to omega, the subobject classifier, in this topos we are working in. And well, I said it. In this category, omega is given as a presheaf of sieves. And one approach to do so, and this is generalizing what Chris and Jeremy Butterfield did in their papers, to define a morphism T sigma, was T psi, sorry, psi, some pure state in the usual sense of some ray in Hilbert space, quantum system, going from subobjects of sigma to omega by simply defining at each stage V, T psi of S, all the subalgebras V prime contained in V, such that this, the projection onto this ray is contained in the corresponding subset of the Gelfand spectrum. Well, here I do identify the subset of the Gelfand spectrum with a projection onto it, so that I can write P psi smaller than or equal to. If you like it more in a physical way, you could say that the expectation value becomes 1. Simply, this is if this ray lies in the subspace, then the expectation value for the corresponding proposition at that stage is 1. And this formulation with the expectation value can be generalized to mixed state. Mixed states, obviously, what is on the level of pure states. This is something one can do, and in fact, well, I want to be careful. I know that if S, which is some subobject of sigma, is of the form delta of P, such a dozenized projection, then this indeed gives a global section of omega, which we would expect as a truth value. If we have some general subobject, I will have to check this, but I think it holds true that we get a global section, and we should get a global section of omega. Well, this is a very strange thing. What I try to sell you here is that if you ask me, is the proposition, the physical quantity A has a value in delta, is it true or not true, or what is it? My answer is, well, it's some global section of omega. It's not yes, it's not no, it's nothing that can be interpreted easily, well, it's what we get. If we take this topos stuff seriously and say we are led to this topos by things like the Cohen-Specker theorem, then we are led to a more general type of logic, and then propositions like A lies in delta are not simply true or false. They are something that there are more truth values, there are more possibilities than that. And, of course, it's a big task to see how we get back to what we usually have, but still this is what we believe may be useful. And at least what we do have is a contextualizer where we take into account all the Wheelan subalgebras, all the different worldviews, if you like. You have no problem if you are within some context, within some worldview. And then we're basically back to the classical world, and everything is fine. But as I said, we want to have a good control of the relations between all these contexts. And this is precisely the fact that we get a global section of omega. It's just the way to control this. And so I have a contextualized type of logic coming from the topos, and yeah, well, this is at this point, this is what I can say about that. But of course we want to do more. We want to say something about self-adjoint operators in some sense also, and so we want to Dasanize them. There is a natural way to do that, which was suggested by De Grote, who was my supervisor in Frankfurt, and he used some interesting thing, namely the fact that one can regard the self-adjoint operators in a phenomenon algebra as a boundedly complete lattice. You wouldn't expect that usually, but you have to consider some different type of order. You don't use the usual order of the self-adjoint operators, but you use something which is called spectral order. I don't have to explain it in detail, but the fact is, if we have some self-adjoint operator A, then we can of course look at the spectral family, all these increasing projections were also in Bob's talk, and then we can, the task will be to adapt the operator also to context where it doesn't lie in, so we have to change the operator in some way. And the suggestion is to do the following. You take all the elements of the all these projections in there, and it may be surprising this is different from what we did before, because here we take the maximum of all of those projections smaller than the given projection, while before we took the infimum of all the projections larger than. In fact, it is the same, because this argument is on the level of spectral families, and if you look, for example, at the spectral family of a projection, then there shows up 1 minus p, p is the projection. So it's just the 1 minus shows up, and so things turn around in some way. This is basically the same thing. If we do this on the level of spectral family to projection, we get exactly what we did to the projection early on directly. So this is not different, though it may seem different.
This is very much, this is a Sasaki hook.
Would be interesting to see that. I don't know, but yeah, okay. And so what we get is a new self-adjoint operator which lies in V as we wanted, and is also approximate A from above, but now in this spectral order. The good thing is, if we now further restrict to some sub-algebras of V, as long as things are commutative, the spectral order and the usual order coincide, they're the same.
What is the spectral order?
Well, you simply say that A is smaller than B if all the elements of the spectral family of A are larger than those, or larger than or equal to those of the spectral family of B. This is something defined on the level of spectral family, so you compare all the projections. The usual order simply is going back to the linear structure.
Yeah.
And moreover, we have something quite nice, which is that the spectrum of AB is contained in the spectrum of A. So, of course, we want to control the spectrum also. And usually, AB need not be a function of A, because we really change the spectral family. We get other projections in the spectral family. This means AB usually is not a function of A. But still, we have good control of what happens to the spectrum, and in fact, it is so that if you look at the spectrum of A and apply some order-preserving function to the spectrum of A itself, you get to AB. This is only one step. What we really want and what we are working on now, this is my last slide, is of course we at the end of the day, we have to talk about real numbers in some sense, because physical quantities are, what we measure are numbers. It just comes down to that. So we will have to say something about that. And so the short and mid-term goals are, of course, a better understanding of physical quantities and states described within a topos, and measure theoretical aspects should come in there. We also have to say something about probabilities. They are not basic, as we believe, to that kind of formalism, and they should show up at some stage. And then, if we succeed with that, and there is some progress, Chris wrote an email last week, I couldn't see him before coming here, but what he said